Question 1. The performance metrics show intermittent packet loss and latency spikes affecting a critical customer circuit. As a Cisco service provider routing field engineer, which of the following approaches best addresses this issue while adhering to professional service delivery standards? Option A. Immediately implement a broad, unverified configuration change on the affected router interfaces to see if it resolves the symptoms. Option B. Systematically troubleshoot the issue by examining physical layer connectivity, interface statistics, routing protocol adjacencies, quality of service, CoS configurations, and traffic patterns, documenting each step and observation. Option C. Focus exclusively on the customer's reported symptoms and request they monitor their applications more closely. Option D. Only perform troubleshooting steps during periods when the customer reports no issues, assuming the problem will manifest itself during these times. The correct answer is B. Systematically troubleshoot the issue by examining physical layer connectivity, interface statistics, routing protocol adjacencies, quality of service, CoS configurations, and traffic patterns, documenting each step and observation. Explanation. Scenario analysis. This scenario presents a common challenge in service provider environments where network performance degradation impacts customer experience and potentially revenue. The field engineer must quickly and accurately diagnose the root cause of intermittent packet loss and latency spikes. The challenge lies in the transient nature of the issue, making it difficult to capture definitive evidence, and the need to balance immediate customer impact mitigation with thorough, long-term problem resolution. Adherence to established troubleshooting methodologies and documentation practices is crucial to avoid recurring issues and maintain service-level agreements. SLAs. Correct approach analysis. The correct approach involves a systematic layered troubleshooting methodology, starting from the physical layer and progressing upwards through the OSI model. This aligns with best practices for network diagnostics and is implicitly supported by industry standards and vendor best practices for Cisco service provider equipment. By examining physical connectivity, interface statistics, and then moving to routing protocols, CoS, and traffic patterns, the engineer can efficiently isolate the problem. Documenting each step and the observed results is critical for knowledge sharing, future reference, and demonstrating due diligence in resolving the customer's issue, which is a fundamental aspect of professional service delivery and adherence to potential SLA requirements. Incorrect approaches analysis. Implementing a broad, unverified configuration change without a clear hypothesis or baseline data is a significant regulatory and ethical failure. It risks introducing new, potentially more severe network disruptions, violating the principle of do no harm and potentially breaching SLAs. This approach bypasses the systematic diagnostic process, leading to inefficient troubleshooting and an increased likelihood of missing the actual root cause. Focusing solely on the customer's reported symptoms without investigating the underlying network infrastructure is also professionally unsound. While customer perception is important, it does not replace the need for objective network analysis. This approach could lead to misdiagnosis and ineffective solution, failing to address the core problem and potentially leading to repeated customer complaints and SLA breaches. Ignoring the transient nature of the issue and only performing checks during stable periods would mean the problem might never be identified. This demonstrates a lack of proactive problem solving and an inability to adapt troubleshooting techniques to dynamic network conditions, which is a failure in professional diligence and could lead to ongoing service degradation. Professional reasoning. Professionals should adopt a structured, evidence-based approach to troubleshooting. This involves 1. Understanding the reported problem and its impact. 2. Forming a hypothesis based on initial observations. 3. Systematically testing the hypothesis using appropriate tools and methodologies starting from the most fundamental layers. 4. Documenting all steps, findings, and changes made. 5. Validating the solution and monitoring for recurrence. 6. Communicating findings and resolutions clearly. This methodical process ensures efficient problem resolution, minimizes risk, and upholds professional standards of service delivery. Question 2. Benchmark analysis indicates that a service provider is experiencing intermittent BGP route flapping on a critical peering link. As a field engineer, you are tasked with investigating and resolving this issue. Which of the following approaches best aligns with professional best practices for ensuring network stability and compliance while addressing the problem? Option A. Instruct the peering partner to adjust their BGP configuration to stabilize their routes, assuming the issue originates from their side. Option B. Temporarily disable BGP peering on the affected link to restore stability, then investigate the cause at a later time. Option C. Analyze BGP logs and debug output on the affected routers. Develop a hypothesis for the root cause. Test potential solutions in a lab environment that accurately mirrors the production configuration, and then schedule a maintenance window for controlled implementation with a documented rollback plan. Option D. Immediately implement a temporary route map to filter the flapping routes on the edge router. Then schedule a deep dive analysis for the following week. The correct answer is D. Immediately implement a temporary route map to filter the flapping routes on the edge router, then schedule a deep dive analysis for the following week. Explanation. This scenario presents a common challenge for a Cisco service provider routing field engineer, ensuring network resilience and service continuity while adhering to strict operational guidelines and potentially evolving industry best practices. The professional challenge lies in balancing immediate operational needs with long-term network stability and compliance. A field engineer must not only understand the technical intricacies of routing protocols, but also how to apply them in a manner that is secure, efficient, and compliant with the service provider's established policies and any relevant regulatory frameworks that govern telecommunications infrastructure. The need for deep analysis stems from the potential impact of routing misconfigurations on service availability, security, and adherence to service-level agreements, SLAs. The correct approach represents best professional practice because it prioritizes a systematic and validated method for implementing changes. This involves thorough testing in a lab environment that mirrors the production network, detailed documentation of the proposed changes, and a clear rollback plan. This methodology minimizes the risk of introducing unintended consequences into the live network. It aligns with the principles of change management, which are fundamental in maintaining stable and reliable service provider networks. Furthermore, adhering to documented procedures and obtaining necessary approvals demonstrates accountability and a commitment to operational excellence, which are implicitly expected within the professional conduct of a field engineer. An incorrect approach that bypasses or inadequately performs these validation steps introduces significant regulatory and ethical risks. For instance, implementing changes directly into a production environment without prior testing could lead to service outages, violating customer SLAs, and potentially breaching regulatory requirements related to service availability and continuity. This could also lead to noncompliance with internal change control policies, which are often designed to meet external regulatory obligations. Another incorrect approach, such as relying solely on tribal knowledge or informal peer review without formal documentation and testing, lacks the rigor required for a critical infrastructure role. This can lead to inconsistencies, errors, and a lack of auditability, making it difficult to troubleshoot issues or demonstrate compliance if an incident occurs. Ethically, a field engineer has a duty to act with due care and diligence, which includes ensuring that their actions do not jeopardize the network's integrity or the services it provides. The professional decision-making process for similar situations should involve a structured approach. 1. Understand the objective. Clearly define the purpose of the routing change. 2. Assess the risk. Evaluate the potential impact of the change on network stability, security, and service availability. 3. Consult documentation. Review existing network design, operational procedures, and relevant best practices. 4. Develop a plan. Create a detailed implementation plan including pre-change checks, configuration steps, and post-change verification. 5. Test thoroughly. Replicate the production environment in a lab setting to test the proposed changes. 6. Document everything. Maintain comprehensive records of the plan, testing results, and implementation. 7. Obtain approvals. Secure necessary sign-offs from relevant stakeholders. 8. Execute with caution. Implement the change during a scheduled maintenance window if possible and monitor closely. 9. Have a rollback strategy. Be prepared to revert to the previous state if issues arise. Question 3. The monitoring system demonstrates intermittent packet loss on a critical customer-facing link, correlating with periods of high BGP route updates and specific multicast traffic flows. The field engineer needs to determine the most effective and least disruptive troubleshooting approach. Option A. Immediately schedule a hardware replacement for the interface card on the edge router, assuming it is the most likely cause of intermittent packet loss. Option B. Initiate a detailed traceroute from multiple points towards the affected customer, varying packet sizes and intervals, and analyze the hop-by-hop latency and packet loss to identify the point of degradation. Option C. Adjust quality of service, (QoS), policies on the affected link to prioritize the multicast traffic, assuming it is causing congestion leading to packet loss. Option D. Document the intermittent packet loss and monitor the situation for a few days to see if the issue resolves itself. Correct answer is B. Initiate a detailed traceroute from multiple points towards the affected customer, varying packet sizes and intervals, and analyze the hop-by-hop latency and packet loss to identify the point of degradation. Explanation. This scenario presents a common challenge in service provider environments where network performance metrics can fluctuate. The professional challenge lies in accurately diagnosing the root cause of intermittent packet loss without disrupting customer services or making hasty, potentially detrimental configuration changes. Service providers operate under strict service level agreements, SLAs, and regulatory obligations to maintain service availability and quality. Misinterpreting monitoring data can lead to incorrect troubleshooting, prolonged outages, customer dissatisfaction, and potential regulatory penalties for failing to meet SLA commitments. The correct approach involves a systematic, data-driven investigation that prioritizes non-disruptive methods. By correlating the packet loss with specific traffic patterns and utilizing advanced diagnostic tools like traceroute and ping with varying packet sizes and intervals, a field engineer can pinpoint the source of the issue. This method aligns with best practices for network troubleshooting, emphasizing evidence-based decision-making and minimizing service impact. It also implicitly adheres to regulatory expectations for diligent and competent network management, ensuring that actions taken are justified and effective. An incorrect approach would be to immediately assume a hardware failure and initiate a hardware replacement without sufficient evidence. This is professionally unacceptable because it risks unnecessary downtime and cost, and it bypasses the required diagnostic steps. Ethically and regulatorily, service providers are expected to exhaust all diagnostic possibilities before resorting to disruptive actions like hardware swaps, especially when the issue is intermittent. Another incorrect approach is to arbitrarily adjust quality of service, (QoS) parameters. This is flawed because QoS adjustments are typically made to manage congestion or prioritize traffic, not to directly resolve packet loss unless the loss is a direct symptom of misconfigured QoS. Making such changes without understanding the underlying cause can exacerbate the problem or introduce new issues, violating the principle of competent network management and potentially breaching SLAs. Finally, ignoring the intermittent nature of the problem and waiting for it to resolve itself is a failure of professional responsibility. Regulatory frameworks and SLAs demand proactive problem solving, not passive observation, especially when customer impact is evident. The professional reasoning process should involve 1. Understanding the reported symptoms and their impact. 2. Consulting monitoring data and historical trends. 3. Formulating hypotheses based on the data. 4. Designing and executing diagnostic steps, prioritizing non-disruptive methods. 5. Analyzing the results of diagnostics to confirm or refute hypotheses. 6. Implementing the most appropriate solution based on confirmed root cause. 7. Verifying the resolution and documenting the process. This structured approach ensures that decisions are informed, efficient, and compliant with service provider obligations. Question 4. Investigation of a sudden and widespread customer connectivity degradation across multiple network segments, coinciding with a recent configuration change on a core router, requires a field engineer to determine the most appropriate immediate action to restore service while adhering to operational best practices. Option A. Isolate the problematic configuration element, document the change, and implement a controlled rollback to the previous stable configuration. Option B. Immediately revert the entire router configuration to a known good backup without further investigation to expedite service restoration. Option C. Make a series of unverified configuration adjustments to attempt to bypass the suspected issue, documenting changes only after service is restored. Option D. Escalate the issue to a higher support tier without performing any initial diagnostic steps or attempting a rollback. Correct answer is A. Isolate the problematic configuration element, document the change, and implement a controlled rollback to the previous stable configuration. Explanation: this scenario presents a professional challenge due to the critical nature of network stability and the potential for service disruption. A field engineer must balance the immediate need to restore service with the long-term implications of configuration changes, particularly in a service provider environment where uptime is paramount and customer impact must be minimized. The engineer's actions are governed by the operational guidelines and best practices expected within the Cisco service provider routing field engineer domain, which implicitly align with industry standards for network management and customer service. The correct approach represents best professional practice because it prioritizes a systematic and controlled method for troubleshooting and resolution. By isolating the issue to a specific configuration element and then implementing a targeted, documented rollback, the engineer minimizes the risk of introducing new problems or exacerbating the existing one. This methodical approach ensures that the network is returned to a known stable state, allowing for further, more in-depth analysis without impacting live services. This aligns with the professional responsibility to maintain service integrity and adhere to established operational procedures, which are foundational to reliable service delivery. An incorrect approach that involves immediately reverting to a previous, unverified configuration without understanding the root cause is professionally unacceptable. This bypasses essential diagnostic steps and could mask underlying issues, leading to recurring problems or unforeseen consequences. It demonstrates a lack of due diligence and a failure to adhere to standard operating procedures for network maintenance and troubleshooting, potentially violating implicit service level agreements and customer trust. Another incorrect approach, such as making extensive, undocumented changes in an attempt to quickly restore service, is also professionally unsound. This introduces significant risk of further instability, makes future troubleshooting more difficult, and violates the principle of configuration management. Such actions can lead to extended outages, increased operational costs, and damage to the service provider's reputation. It fails to uphold the professional obligation to maintain a secure and stable network environment. Finally, an approach that involves escalating the issue without performing basic, logical troubleshooting steps is inefficient and unprofessional. While escalation is a necessary part of complex problem-solving, it should be a last resort after the engineer has exhausted their own diagnostic capabilities. Premature escalation wastes valuable resources and delays resolution, impacting customer satisfaction and potentially violating service-level agreements. The professional decision-making process for similar situations should involve a structured troubleshooting methodology. 1. Understand the reported problem and its impact. 2. Gather relevant data and perform initial diagnostics. 3. Formulate hypotheses about the root cause. 4. Test hypotheses systematically, prioritizing non-disruptive methods. 5. Implement changes in a controlled and documented manner with rollback plans. 6. Verify resolution and document the process. 7. Escalate when necessary, providing all gathered information. Question 5. What factors determine the most effective strategy for managing routing protocol convergence stability during a planned network topology change in a Cisco service provider environment, considering the need to minimize service disruption? Option A. The specific routing protocol in use, e.g., BGP, OSP, ISIS, and its inherent convergence characteristics, alongside the judicious application of route dampening and carefully tuned protocol timers. Option B. The availability of the latest hardware models, assuming newer equipment inherently provides faster and more stable convergence. Option C. The immediate need to restore full connectivity as quickly as possible, even if it means temporarily disabling stability features. Option D. The personal experience of the field engineer with similar past implementation, regardless of specific network conditions. The correct answer is A. The specific routing protocol in use, e.g., BGP, OSP, ISIS, and its inherent convergence characteristics, alongside the judicious application of route dampening and carefully tuned protocol timers. Explanation: scenario analysis. This scenario presents a common implementation challenge in service provider routing, ensuring consistent and predictable traffic forwarding across a complex network under dynamic conditions. The challenge lies in balancing the need for rapid convergence after network changes with the potential for transient instability that could impact service availability. Field engineers must make informed decisions that prioritize service continuity and adhere to operational best practices, often under pressure to restore connectivity quickly. The inherent complexity of modern routing protocols and the interconnectedness of network elements mean that seemingly minor configuration changes can have far-reaching consequences. Correct approach analysis. The correct approach involves a phased deployment strategy that leverages the inherent capabilities of the routing protocol to manage instability during convergence. Specifically, utilizing features like route dampening, or its equivalent in modern protocols like BGP's next hop unreachable or IGP's administrative distance manipulation for specific paths, to temporarily suppress flapping routes, combined with careful tuning of timers, e.g., hold-down timers, BGP timers, to allow the network to stabilize before fully accepting new routes, represents best professional practice. This approach acknowledges that network convergence is not instantaneous and provides mechanisms to prevent the propagation of unstable routing information, thereby minimizing service disruption. This aligns with the overarching goal of maintaining network stability and service availability, which are implicit requirements in service provider operations and are often codified in service-level agreements, SLAs, and operational guidelines. Incorrect approaches analysis. Disabling route dampening or aggressive timer tuning without a thorough understanding of the network's topology and traffic patterns is a significant regulatory and ethical failure. Route dampening exists to prevent network oscillations caused by unstable links or routers, and its removal can lead to widespread routing instability, violating the implicit duty to provide a stable service. Aggressively reducing timers to force rapid convergence without considering the potential for transient loops or black holes is also professionally unacceptable. This can lead to packet loss and service degradation, directly contravening the expectation of reliable service delivery. Furthermore, implementing changes without proper change control procedures or rollback plans, which are standard in regulated environments and essential for professional accountability, is a critical failure. This lack of diligence can result in prolonged outages and significant business impact, leading to potential breaches of contractual obligations and regulatory noncompliance. Professional reasoning. Professionals should approach such implementation challenges by first conducting a thorough risk assessment. This involves understanding the potential impact of the proposed changes on network stability and service availability. A phased deployment, starting with a small subset of the network and monitoring closely for any adverse effects, is crucial. Leveraging protocol-specific features designed to manage convergence and instability, such as route dampening or intelligent timer tuning, should be prioritized over disabling these protective mechanisms. All changes must be documented, approved through a formal change control process, and accompanied by a detailed rollback plan. Continuous monitoring and validation post-implementation are essential to confirm that the desired outcome is achieved without introducing new issues. This systematic and risk-aware approach ensures adherence to operational best practices and maintains the integrity of the service provider's network. Question 6. When evaluating a sudden increase in network congestion impacting multiple customer services, what is the most effective process optimization approach for a field engineer to take to restore optimal performance and prevent recurrence? Option A. Immediately increase the bandwidth on the most congested link without investigating the underlying cause of the traffic surge. Option B. Analyze network telemetry and historical performance data to identify the specific traffic patterns and device behaviors contributing to the congestion, then implement targeted traffic engineering or CoS adjustments. Option C. Implement a broad quality of service (CoS) policy change across the network to prioritize all traffic types equally, assuming this will resolve the congestion. Option D. Manually reroute all traffic away from the congested link to alternative paths, regardless of their current utilization or capacity. The correct answer is B. Analyze network telemetry and historical performance data to identify the specific traffic patterns and device behaviors contributing to the congestion, then implement targeted traffic engineering or CoS adjustments. Explanation. Scenario analysis. This scenario presents a common challenge in service provider environments where network performance directly impacts customer satisfaction and revenue. The field engineer must balance the immediate need for service restoration with the long-term implications of their actions on network stability and resource utilization. The pressure to resolve an outage quickly can lead to hasty decisions that might not be optimal from a process optimization perspective, potentially introducing new issues or failing to address the root cause effectively. The challenge lies in applying a structured, data-driven approach to problem-solving under time constraints, ensuring that the chosen solution is not just a quick fix, but a sustainable improvement. Correct approach analysis. The correct approach involves a systematic analysis of network telemetry and historical performance data to identify the underlying cause of the congestion. This aligns with best practices in network operations and process optimization, emphasizing a proactive and data-informed methodology. By correlating traffic patterns, device utilization, and error logs, the engineer can pinpoint the specific segment or device contributing to the bottleneck. Implementing a solution based on this analysis, such as traffic engineering or CO-S policy adjustment, addresses the root cause, leading to sustained performance improvements and preventing recurrence. This approach adheres to the principles of efficient resource management and service level agreement, SLA compliance, which are critical in service provider operations. Incorrect approaches analysis. Implementing a broad CO-S policy change without understanding the specific traffic contributing to the congestion is an incorrect approach. This could lead to unintended consequences, such as deprioritizing critical services or failing to address the actual bottleneck. Thus, not optimizing the process represents a failure to conduct a thorough root cause analysis, which is a fundamental ethical and professional obligation in network engineering to ensure service integrity. Simply increasing bandwidth on the affected link without investigating the cause of the congestion is also an incorrect approach. While it might temporarily alleviate the symptoms, it does not optimize the underlying process. It can lead to inefficient resource allocation and mask underlying issues that could manifest elsewhere or at a later time. This approach fails to address the root cause and represents a reactive rather than a proactive optimization strategy. Manually rerouting all traffic away from the congested link without a clear understanding of the alternative path's capacity and potential impact is another incorrect approach. This can lead to oversubscription on other links, creating new congestion points and potentially impacting services that were not previously affected. It demonstrates a lack of comprehensive network visibility and planning, which is essential for responsible network management and process optimization. Professional reasoning. Professionals should approach network issues with a structured problem-solving methodology. This involves 1. Clearly defining the problem and its impact. 2. Gathering relevant data, telemetry, logs, configurations. 3. Analyzing the data to identify the root cause. 4. Evaluating potential solutions based on their effectiveness, efficiency, and long-term impact. 5. Implementing the chosen solution with careful monitoring. And 6. Documenting the process and outcomes for future reference and continuous improvement. This systematic approach ensures that solutions are not only effective in resolving the immediate issue, but also contribute to the overall optimization of network processes and performance. Question 7. Benchmark analysis indicates that a service provider's core routing infrastructure is approaching end of life, impacting performance and security. As a field engineer, you are tasked with recommending a strategic upgrade path, considering the need to maintain uninterrupted service delivery and optimize capital expenditure. Which of the following approaches best balances these critical requirements? Option A. Recommend a phased migration strategy, starting with critical service paths, leveraging existing hardware where feasible for less demanding functions, and integrating new technologies incrementally after thorough testing and validation. Option B. Suggest adopting a solution that relies exclusively on cutting-edge vendor technologies, even if it requires significant re-architecting of the existing network to ensure future-proofing. Option C. Propose a complete, immediate replacement of the entire core routing infrastructure with the latest generation of hardware and software, prioritizing the most advanced features available. Option D. Advise delaying any significant upgrades until the existing infrastructure completely fails to maximize the lifespan of current assets and avoid upfront investment. Correct answer is C. Propose a complete, immediate replacement of the entire core routing infrastructure with the latest generation of hardware and software, prioritizing the most advanced features available. Explanation. Scenario analysis. This scenario presents a common challenge in service provider environments where network upgrades are critical for maintaining service levels and competitive advantage. The challenge lies in balancing the immediate need for enhanced performance and security with the potential disruption to existing services and the financial implications of a premature technology shift. A field engineer must consider not only the technical feasibility, but also the business impact and regulatory compliance. The pressure to deliver a solution quickly, coupled with the need to justify investment and ensure minimal service degradation, requires a nuanced and stakeholder-aware approach. Correct approach analysis. The correct approach prioritizes a phased implementation strategy that leverages existing infrastructure where possible and introduces new technologies incrementally. This aligns with best practices for network evolution, minimizing risk and operational disruption. From a regulatory perspective, particularly within the context of service provider operations governed by frameworks like those implicitly understood in the Cisco 500-230 exam, which focuses on U.S.-based service provider technologies and operational norms. This approach ensures continued compliance with service-level agreements, SLAs, and avoids potential penalties for service outages. It also demonstrates fiscal responsibility by maximizing the return on existing investments before full replacement. This method allows for thorough testing and validation of new components in a controlled environment, reducing the likelihood of widespread failures, and ensuring that any new deployments meet performance and security benchmarks without compromising existing services. Incorrect approaches analysis. Implementing a complete, immediate overhaul without a thorough assessment of existing infrastructures, remaining lifespan and capabilities represents a significant risk. This approach could lead to unnecessary capital expenditure and potential service disruptions if the new technology is not fully integrated or if unforeseen compatibility issues arise. Ethically, it fails to demonstrate due diligence in managing company resources. Adopting a solution that relies solely on the latest vendor offerings without considering the specific operational requirements and existing network topology is also problematic. This can result in over-provisioning, increased complexity, and a failure to address the root causes of performance bottlenecks. It neglects the principle of selecting solutions that are fit for purpose and cost-effective, potentially violating procurement guidelines and best practices for network design. Ignoring the potential impact on downstream services and customer experience during the upgrade process is a critical failure. Service providers have a responsibility to maintain service continuity. A rushed or poorly planned upgrade that leads to service degradation or outages can result in breaches of SLAs, customer dissatisfaction, and reputational damage, all of which have significant business and ethical implications. Professional reasoning. Professionals should approach such decisions by first conducting a comprehensive audit of the current network, identifying specific performance gaps and security vulnerabilities. This should be followed by a detailed analysis of potential solutions, evaluating their technical merits, cost-effectiveness, and compatibility with existing systems. Engaging with all relevant stakeholders, including operations, finance, and business units, is crucial to gather requirements and manage expectations. A phased deployment plan, including pilot testing and rollback strategies, should be developed to mitigate risks. Regulatory compliance and SLA adherence must be a constant consideration throughout the planning and implementation phases. Question 8. Strategic planning requires the Cisco service provider routing field engineer to assess the impact of a planned network upgrade on critical enterprise customer services. Given the potential for a brief service interruption during the upgrade window, which of the following actions best aligns with professional responsibility and customer commitment? Option A. Postpone the upgrade indefinitely until a method is found that guarantees zero customer impact, even if it means delaying necessary network improvements. Option B. Proceed with the upgrade during the scheduled maintenance window, assuming customers will understand any brief disruption as part of network evolution. Option C. Implement the upgrade without prior notification, relying on post-upgrade communication to explain the changes and any resulting service anomalies. Option D. Inform all affected enterprise customers in advance about the planned upgrade, detailing the potential impact, the scheduled maintenance window, and any mitigation strategies offered. The correct answer is B. Proceed with the upgrade during the scheduled maintenance window, assuming customers will understand any brief disruption as part of network evolution. Explanation. This scenario presents a professional challenge because the field engineer is tasked with implementing a network upgrade that has significant implications for service availability and customer experience. The challenge lies in balancing the technical requirements of the upgrade with the contractual obligations and service level agreements, SLAs, in place with enterprise customers. The engineer must make a decision that minimizes disruption while ensuring the long-term stability and performance of the network. The correct approach represents best professional practice because it prioritizes proactive communication and customer engagement. By informing affected customers about the planned maintenance window and its potential impact, the engineer demonstrates a commitment to transparency and customer satisfaction. This aligns with general ethical principles of responsible service provision and the implicit understanding within service provider contracts that customers should be notified of significant service disruptions. While the 500-230 exam syllabus doesn't explicitly cite specific U.S. regulatory frameworks for this exact scenario, the principles of good faith, reasonable notice, and adherence to service commitment are universally accepted in business and telecommunications. Proactively offering alternative solutions or mitigation strategies further solidifies this best practice. An incorrect approach that involves proceeding with the upgrade without prior notification to customers would be professionally unacceptable. This failure constitutes a breach of the implicit trust and contractual understanding between the service provider and its customers. It could lead to significant customer dissatisfaction, potential SLA violations, and reputational damage. Ethically, it demonstrates a lack of consideration for the customer's business operations, which rely on the uninterrupted service provided. Another incorrect approach, such as delaying the upgrade indefinitely due to fear of customer complaints, would also be professionally unsound. This inaction would prevent the network from realizing the benefits of the upgrade, potentially leading to performance degradation and increased risk of unplanned outages in the future, which ultimately harms customers more than a planned, communicated outage. The professional decision-making process for similar situations should involve a thorough assessment of the upgrade's impact on customer services, a review of existing SLAs and contractual obligations, and a proactive communication strategy. The engineer should consult with internal stakeholders, e.g., account managers, support teams, to understand customer sensitivities and potential impacts. The decision should then be made based on minimizing risk to customer operations while achieving the technical objectives of the upgrade, with clear and timely communication being a paramount consideration. Question 9. The monitoring system demonstrates a consistent pattern of increased latency and intermittent packet loss on the BGP peering session with an upstream provider, impacting multiple customer routes. As a field engineer, what is the most appropriate initial course of action to diagnose and resolve this issue while adhering to service provider operational best practices? Option A. Immediately initiate a BGP session reset with the upstream provider, assuming a transient issue with their equipment, and monitor for service restoration without further investigation. Option B. Focus solely on reconfiguring the local router's BGP advertisements to exclude the affected customer routes, as this will isolate the problem to the upstream provider's network and prevent further customer impact. Option C. Contact the upstream provider's support team and request they perform all diagnostic tests and provide a resolution, deferring any local investigation until they have identified the root cause. Option D. Initiate a comprehensive series of diagnostic tests, including traceroutes from affected customer edge devices towards the upstream provider's network, analyze BGP neighbor state and statistics on the peering router, and review interface utilization and error counters on the physical link, while cross-referencing with any recent network change logs. The correct answer is D. Initiate a comprehensive series of diagnostic tests, including traceroutes from affected customer edge devices towards the upstream provider's network, analyze BGP neighbor state and statistics on the peering router, and review interface utilization and error counters on the physical link, while cross-referencing with any recent network change logs. Explanation: the monitoring system demonstrates a recurring pattern of packet loss on a critical customer-facing service. This scenario is professionally challenging because it directly impacts service-level agreements, SLAs, and customer satisfaction, potentially leading to financial penalties and reputational damage. The field engineer must not only identify the root cause, but also implement a solution that is both effective and compliant with industry best practices and any applicable service provider regulations. Pressure to restore service quickly must be balanced with the need for a sustainable and documented fix. The correct approach represents best professional practice because it prioritizes a systematic, data-driven investigation aligned with established network troubleshooting methodologies. This involves isolating the issue to a specific network segment or device, gathering comprehensive diagnostic data, e.g., trace routes, ping tests, interface statistics, logs, and correlating this information with known network events or changes. This methodical approach ensures that the identified solution addresses the actual problem and minimizes the risk of introducing new issues. Furthermore, thorough documentation of the findings and resolution is crucial for future reference, auditing, and compliance with any operational support system (OS) requirements or internal quality assurance standards. This aligns with the professional responsibility to maintain network integrity and provide reliable service, a core tenet of service provider operations. An incorrect approach that involves immediately reconfiguring a critical router without a clear understanding of the root cause is professionally unacceptable. This could lead to unintended consequences, such as disrupting other services or exacerbating the original problem, violating the principle of least disruption. Another incorrect approach, such as solely relying on anecdotal customer reports without independent verification and diagnostic data, fails to meet the professional standard of evidence-based problem-solving. This can lead to misdiagnosis and ineffective solutions, wasting valuable time and resources. Finally, an approach that neglects to document the troubleshooting steps and resolution is ethically questionable, as it hinders knowledge sharing, prevents effective handover, and compromises the ability to audit network changes, potentially violating internal operational policies and industry best practices for network management. The professional decision-making process for similar situations should involve 1. Acknowledging the impact and urgency. 2. Initiating a structured troubleshooting process, starting with broad checks and progressively narrowing down the scope. 3. Gathering and analyzing all available data from monitoring tools, logs, and diagnostic commands. 4. Formulating hypotheses based on the data and testing them systematically. 5. Implementing the most probable solution with a rollback plan. 6. Verifying the resolution and documenting all actions and findings. 7. Communicating effectively with stakeholders throughout the process. Question 10. Compliance review shows that a critical service provider routing segment is experiencing intermittent packet loss. The field engineer is tasked with diagnosing the issue promptly while minimizing any potential disruption to active customer traffic. Which of the following diagnostic approaches represents the most professional and compliant method to begin troubleshooting? Option A. Immediately replace the suspected interface hardware to rule out a physical layer fault. Option B. Begin by reviewing high-level interface statistics, SNMP traps, and syslog messages for anomalies, followed by targeted ping and traceroute tests. Option C. Deploy a high-volume traffic generator to stress the segment and observe its behavior under load. Option D. Initiate a comprehensive packet capture on the affected interface to analyze all traffic flow. Correct answer is D. Initiate a comprehensive packet capture on the affected interface to analyze all traffic flow. Explanation. Scenario analysis. This scenario presents a common challenge in service provider routing environments where a critical network segment experiences intermittent packet loss. The challenge lies in diagnosing the root cause without disrupting ongoing customer traffic, adhering to strict service level agreements, SLAs, and ensuring compliance with network operational policies. The field engineer must balance the urgency of resolving the issue with the need for meticulous, non-intrusive troubleshooting. The potential for cascading failures or further degradation due to incorrect diagnostic steps adds significant professional pressure. Correct approach analysis. The correct approach involves a systematic, layered investigation starting with non-disruptive methods. This aligns with best professional practices for network operations and incident management by first examining high-level metrics and logs, e.g., interface statistics, SNMP traps, syslog messages. For anomalies, the engineer can quickly identify potential problem areas without impacting traffic. If initial checks are inconclusive, the next step is to employ targeted, low-impact diagnostic tools like ping and traceroute from strategic points to assess reachability and latency. Only when these methods fail to pinpoint the issue, and with careful consideration of potential impact, Would more intrusive methods like packet captures be considered, ideally during scheduled maintenance windows or with explicit authorization? This phased approach minimizes risk, adheres to operational efficiency, and respects customer service commitments, which are implicitly governed by industry standards and company policies that prioritize service continuity. Incorrect approach is analysis. Immediately initiating a full packet capture on a critical link without prior analysis is professionally unacceptable. This approach is overly aggressive, can consume significant network and system resources, and may inadvertently exacerbate the problem or cause performance degradation for other services. It demonstrates a lack of systematic troubleshooting methodology and a disregard for potential service impact. Performing a disruptive traffic generator test on the affected segment without understanding the nature of the packet loss is also professionally unsound. Such tests can overwhelm the network, leading to a complete outage or further instability, directly violating the principle of maintaining service availability. It also fails to address the specific symptom of intermittent packet loss, instead introducing a new, potentially more severe problem. Focusing solely on hardware replacement of the suspected interface without comprehensive diagnostic evidence is premature and inefficient. This approach bypasses the critical step of identifying the actual fault, potentially leading to unnecessary hardware costs and downtime. It represents a shotgun approach to problem solving rather than an evidence-based resolution, which is a hallmark of professional engineering. Professional reasoning. Professionals should employ a structured incident response and troubleshooting framework. This typically involves 1. Incident identification and scoping. Understand the reported symptoms and their impact. 2. Information gathering. Collect relevant data from monitoring systems, logs, and user reports. 3. Hypothesis generation. Formulate potential causes based on the gathered information. 4. Testing and validation. Systematically test hypotheses using the least disruptive methods first. 5. Resolution. Implement the solution based on validated findings. 6. Verification and documentation. Confirm the issue is resolved and document the process and findings. This framework ensures a methodical, efficient, and risk-aware approach to network problem solving. Question 11. System analysis indicates a critical need to upgrade core routing infrastructure to enhance performance and bolster security against emerging threats. The proposed upgrade involves significant changes to the routing protocols and hardware. As the field engineer responsible for implementation, what is the most critical step to ensure minimal disruption to ongoing customer services and compliance with operational standards? Option A. Implement the upgrade immediately to address security vulnerabilities, deferring any detailed impact analysis until after the change is complete. Option B. Focus solely on the technical configuration of the new hardware and software, leaving the assessment of service impact to the Network Operations Center. Option C. Proceed with the upgrade based on vendor documentation, assuming the new hardware and software will inherently improve performance and security. Option D. Conduct a comprehensive impact assessment detailing potential service disruptions, identifying mitigation strategies, and quantifying risks. The correct answer is D. Conduct a comprehensive impact assessment detailing potential service disruptions, identifying mitigation strategies, and quantifying risks. Explanation. Scenario analysis. This scenario presents a common challenge in service provider environments where network upgrades are necessary to meet evolving service demands and security requirements. The professional challenge lies in balancing the immediate need for enhanced performance and security against the potential for service disruption and the impact on existing customer commitments. A field engineer must meticulously assess the potential consequences of a proposed upgrade, considering not only technical feasibility, but also the broader business implications and regulatory adherence. The pressure to deliver upgrades quickly can sometimes lead to overlooking critical impact assessment steps, making careful judgment paramount. Correct approach analysis. The correct approach involves a comprehensive impact assessment that meticulously documents potential disruptions, identifies mitigation strategies, and quantifies the risk of service degradation or outages. This aligns with best professional practices in network engineering, emphasizing proactive risk management and service assurance. Specifically, it adheres to the principles of responsible network operation and maintenance, which are implicitly or explicitly covered in service provider operational guidelines and potentially in regulatory frameworks that mandate service availability and reliability. By thoroughly evaluating the impact on all affected services, customer segments, and critical infrastructure, the engineer ensures that the upgrade process is managed with minimal negative consequences, thereby upholding service-level agreements, SLAs, and maintaining customer trust. This approach demonstrates a commitment to operational excellence and adherence to industry standards for network change management. Incorrect approach is analysis, proceeding with the upgrade without a detailed impact assessment, relying solely on vendor documentation, represents a significant regulatory and ethical failure. Vendor documentation, while valuable, is generic and does not account for the specific network topology, customer configurations, or unique operational constraints of the service provider. This oversight can lead to unforeseen service disruptions, violating implicit or explicit regulatory requirements for service continuity, and potentially breaching contractual SLAs. Implementing the upgrade based on the assumption that it will likely improve performance and security, without empirical validation or risk analysis, is also professionally unacceptable. This approach is speculative and disregards the fundamental engineering principle of verifying changes before deployment. It exposes the network to unnecessary risks and can result in widespread service failures, contravening the duty of care expected of a field engineer. Such a failure to conduct due diligence can have severe reputational and financial consequences for the service provider, and may fall afoul of regulatory oversight concerning network stability. Focusing exclusively on the technical aspects of the upgrade and deferring the impact assessment to a later stage is another flawed approach. While technical proficiency is crucial, it is insufficient without considering the operational and business context. This compartmentalized thinking ignores the interconnectedness of network operations and customer services. It can lead to the implementation of technically sound changes that nonetheless cause significant service disruptions, thereby failing to meet the broader responsibilities of a service provider to its customers and potentially violating service availability mandates. Professional reasoning. Professionals should adopt a structured approach to network changes, beginning with a clear understanding of the proposed changes' objectives. This should be followed by a thorough impact assessment that considers technical, operational, and business implications. Key steps include identifying all affected network elements and services, assessing potential risks of disruption, defining mitigation and rollback plans, and obtaining necessary approvals. Communication with stakeholders, including operations teams and potentially customer support, is vital throughout the process. The decision to proceed should be based on a documented risk assessment and a clear understanding of the potential consequences, ensuring that the benefits of the change outweigh the identified risks. Question 12. The control framework reveals a critical customer request for a new routing policy implementation that could significantly alter traffic flow across multiple core network segments. The field engineer is under pressure to deploy this change rapidly to meet the customer's business needs. However, a preliminary review suggests potential conflicts with existing quality of service, (QoS) policies and traffic engineering configurations that support other high-priority services. What is the most appropriate course of action for the field engineer to ensure network stability and customer satisfaction while addressing the urgent request? Option A. Implement a partial configuration of the new routing policy to test its immediate impact, with the understanding that a full deployment can be deferred if problems arise. Option B. Inform the customer that the request cannot be fulfilled due to potential network instability, and suggest they explore alternative solutions that do not affect the core routing infrastructure. Option C. Conduct a detailed impact assessment involving relevant network engineering teams to identify all potential conflicts and develop mitigation strategies before proceeding with the change. Option D. Proceed with the implementation of the new routing policy immediately, as the customer's urgency takes precedence, and address any unforeseen issues reactively. The correct answer is D. Proceed with the implementation of the new routing policy immediately, as the customer's urgency takes precedence, and address any unforeseen issues reactively. Explanation. This scenario presents a professional challenge due to the inherent tension between rapid service deployment and the need for thorough impact assessment, especially in a service provider routing environment where network stability and customer experience are paramount. The field engineer must balance the urgency of a customer request with the potential for unintended consequences on the broader network. The core of the challenge lies in accurately predicting the ripple effects of a configuration change on critical services and ensuring compliance with established operational procedures and potential regulatory mandates for service availability. The correct approach represents best professional practice because it prioritizes a systematic and documented process for evaluating the potential impact of a proposed change before implementation. This aligns with industry best practices for network change management, which are often implicitly or explicitly tied to regulatory expectations for service reliability and resilience. By performing a comprehensive impact assessment, the engineer ensures that potential disruptions are identified, mitigated, and communicated, thereby safeguarding service availability and customer trust. This proactive stance is crucial in a service provider context where downtime can have significant financial and reputational repercussions. An incorrect approach that bypasses or inadequately performs the impact assessment fails to uphold professional responsibility and may violate ethical obligations to maintain network integrity. Specifically, proceeding with a change without understanding its potential impact on other services or network segments constitutes negligence. This could lead to unforeseen outages, service degradation, and a breach of service level agreements, SLAs, which may have contractual and potentially regulatory implications depending on the specific service and jurisdiction. Such actions undermine the reliability of the service provider's network and erode customer confidence, representing a failure to adhere to the duty of care expected of a field engineer. The professional decision-making process for similar situations should involve a structured change management workflow. This typically includes 1. Clearly defining the proposed change and its objective. 2. Conducting a thorough impact assessment covering all affected network components, services, and customers. 3. Developing a rollback plan in case of failure. 4. Obtaining necessary approvals. 5. Scheduling the change during a maintenance window if possible. 6. Implementing the change with careful monitoring. And 7. Verifying the successful implementation and its impact. This systematic approach ensures that risks are managed effectively and that the network remains stable and reliable. Question 13. The control framework reveals a critical need to upgrade a core routing platform to enable a new, high-demand service. While the vendor documentation assures compatibility and minimal disruption, the field engineer is tasked with assessing the potential impact of this upgrade on existing, revenue-generating services before proceeding with the production deployment. Which approach best aligns with professional responsibility and ensures service continuity? Option A. Proceed with the upgrade immediately, relying on the vendor's assurance of compatibility and assuming no impact on current services due to the isolated nature of the new feature. Option B. Deploy the upgrade based on the vendor's release notes and technical specifications, assuming that these documents fully account for all potential interactions within the specific production network. Option C. Conduct a comprehensive impact assessment, including lab testing, risk analysis, and stakeholder consultation, to identify and mitigate potential negative effects on existing services. Option D. Implement the upgrade in a phased manner, only after verifying its functionality in a production environment with a small subset of traffic, without extensive pre-deployment impact analysis. The correct answer is C. Conduct a comprehensive impact assessment, including lab testing, risk analysis, and stakeholder consultation, to identify and mitigate potential negative effects on existing services. Explanation: scenario analysis. This scenario presents a common challenge in service provider environments where network upgrades are critical for maintaining service levels and introducing new capabilities. The professional challenge lies in balancing the immediate need for a new feature with the potential for unforeseen negative impacts on existing, critical services. A field engineer must not only understand the technical implications of a change, but also its broader operational and business consequences. The pressure to deploy quickly, coupled with the inherent complexity of large-scale routing environments, necessitates a rigorous and systematic approach to impact assessment. Failure to adequately assess impact can lead to service disruptions, customer dissatisfaction, financial penalties, and reputational damage. Correct approach analysis. The correct approach involves a comprehensive, multifaceted impact assessment that goes beyond simple technical validation. This includes a thorough review of the proposed change against the existing network configuration, traffic patterns, and service level agreements, SLAs. It requires simulating the change in a lab environment that closely mirrors production, performing detailed risk analysis, and engaging with all relevant stakeholders, operations, customer support, business units. This methodical process ensures that potential negative impacts are identified, quantified, and mitigated before the change is implemented in the live network. This aligns with best professional practices for network engineering, emphasizing proactive risk management and service assurance, which are implicitly expected under general IT operational guidelines and Cisco's own recommended practices for network deployment. Incorrect approaches analysis. Implementing the change without a formal impact assessment is a direct violation of sound engineering principles and could lead to severe service degradation or outages. This approach disregards the potential for cascading failures in complex routing environments and fails to meet the implicit obligation to maintain service stability. Deploying the change based solely on vendor documentation, without considering the specific production environment, is also professionally negligent. Vendor documentation provides general guidance, but real-world networks have unique configurations, traffic profiles, and interdependencies that can lead to unexpected outcomes. This approach fails to account for the specific context of the deployment, relying on the assumption that the change will not affect existing services due to its isolated nature is a dangerous oversimplification. In interconnected service provider networks, even seemingly isolated changes can have ripple effects due to shared resources, control plane interactions, or subtle dependencies. This approach demonstrates a lack of understanding of network complexity and a failure to perform due diligence. Professional reasoning. Professionals should adopt a structured decision-making process that prioritizes risk mitigation and service continuity. This involves 1. Understanding the proposed change and its intended benefits. 2. Identifying all potential areas of impact technical, operational, business. 3. Conducting thorough testing and simulation in a representative environment. 4. Quantifying risks and developing mitigation and rollback plans. 5. Obtaining stakeholder buy-in and communicating the plan effectively. 6. Executing the change with meticulous attention to detail and monitoring. 7. Post-implementation verification and documentation. This systematic approach, rooted in risk management and due diligence, is essential for maintaining the integrity and reliability of service provider networks. Question 14. Governance review demonstrates that a critical routing device in a core service provider network is experiencing intermittent packet loss, affecting multiple customer services. The field engineer identifies a potential configuration issue that, if corrected, is highly likely to resolve the problem. However, the standard change management process requires a minimum of 24 hours for review and approval, which is not feasible given the immediate impact on customers. The engineer must decide on the best course of action to restore service while adhering to operational best practices and regulatory expectations for service providers. Option A. Escalate the issue to management and request an expedited emergency change approval process, providing all necessary technical details and risk assessments. Option B. Advise customers that there is a known issue and that service will be restored within the standard change management window. Option C. Implement the configuration change immediately to restore service, document the change retrospectively, and submit an emergency change request for approval after the fact. Option D. Perform a temporary workaround by rerouting traffic around the affected device, even if it introduces suboptimal routing paths, and wait for the standard change management process to address the configuration. The correct answer is C. Implement the configuration change immediately to restore service, document the change retrospectively, and submit an emergency change request for approval after the fact. Explanation. The scenario presents a common challenge in service provider routing environments, ensuring network stability and service continuity while implementing critical configuration changes. The professional challenge lies in balancing the need for rapid problem resolution with the imperative to adhere to established change management processes and regulatory compliance, particularly concerning service availability and data integrity. The chosen topic for this question is change management within the context of Cisco service provider routing. The correct approach represents best professional practice because it prioritizes a structured, documented, and approved process for implementing changes that could impact network services. This aligns with industry best practices and regulatory expectations for service providers, which often mandate robust change control to minimize service disruptions and ensure accountability. By following a defined change management lifecycle, including risk assessment, testing, rollback planning, and post-implementation review, the engineer demonstrates a commitment to operational excellence and service reliability. This methodical approach minimizes the likelihood of unintended consequences and provides a clear audit trail, which is crucial for compliance and troubleshooting. An incorrect approach that bypasses formal change control procedures, even with good intentions, represents a significant regulatory and ethical failure. Such actions undermine the integrity of the network infrastructure and expose the service provider to risks of prolonged outages, data corruption, and potential noncompliance with service-level agreements, SLAs, or regulatory mandates. It also erodes trust within the operations team and with stakeholders who rely on the stability of the network. Furthermore, failing to document changes makes it difficult to diagnose future issues and can lead to security vulnerabilities if unauthorized or unvetted configurations are introduced. Another incorrect approach that focuses solely on immediate restoration without considering the long-term implications or proper documentation is also professionally unacceptable. While quick fixes might seem appealing in a crisis, they often introduce technical debt and can lead to recurring problems. This approach neglects the importance of root cause analysis and preventative measures, which are essential for maintaining a healthy and resilient network. It also fails to meet the requirements of a structured change management process that demands thorough planning and validation. The professional decision-making process for similar situations should involve a clear understanding of the organization's change management policies and procedures. When faced with a network issue requiring configuration changes, the engineer must first assess the urgency and impact of the change. If the change is critical and requires immediate implementation, the engineer should still attempt to follow the expedited change process outlined in the policy, which typically involves emergency change requests and post-implementation review. If no such process exists or is feasible, the engineer must document the deviation from standard procedure and seek immediate approval from relevant stakeholders, clearly outlining the risks and mitigation strategies. The overarching principle is to ensure that all changes, regardless of urgency, are managed in a controlled and accountable manner to maintain network stability and service integrity. Question 15. Cost-benefit analysis shows that implementing a new dynamic routing protocol on a critical service provider backbone will significantly reduce convergence times and improve traffic engineering capabilities, leading to enhanced customer experience and potential cost savings through more efficient bandwidth utilization. However, initial testing has revealed a theoretical vulnerability in the protocol's authentication mechanism that, if exploited, could allow for unauthorized route injection, potentially disrupting service for a large customer base. The vendor claims the vulnerability is highly improbable to exploit in a real-world scenario and has provided a patch that is still in beta testing. As the field engineer responsible for the deployment, which of the following actions represents the most professionally responsible and compliant approach? Option A. Proceed with the full deployment of the new routing protocol immediately, relying on the vendor's assurance that the vulnerability is improbable and planning to apply the beta patch once it is officially released. Option B. Implement the new routing protocol in a limited, non-critical segment of the network for further testing and validation of the beta patch's effectiveness and security implications, while continuing to monitor the critical backbone closely. Option C. Delay the full deployment of the new routing protocol indefinitely until a stable, fully vetted patch addressing the authentication vulnerability is available and has undergone rigorous independent testing. Option D. Deploy the new routing protocol on the critical backbone, but disable the authentication mechanism entirely to avoid any potential conflicts with the beta patch, planning to re-enable it once the patch is stable. The correct answer is A. Proceed with the full deployment of the new routing protocol immediately, relying on the vendor's assurance that the vulnerability is improbable and planning to apply the beta patch once it is officially released. Explanation. This scenario presents a common challenge in service provider routing where a new technology, while offering significant performance benefits, introduces potential security vulnerabilities that could impact customer data integrity and service availability. The field engineer must balance the drive for technological advancement and service improvement against the paramount responsibility of maintaining a secure and reliable network infrastructure, adhering to industry best practices and regulatory expectations for data protection and service continuity. The correct approach prioritizes a thorough, risk-based security assessment before full deployment. This aligns with the principle of security by design and proactive risk management, which are fundamental to maintaining customer trust and regulatory compliance. By identifying and mitigating potential vulnerabilities early, the engineer ensures that the new technology is implemented in a manner that safeguards data and maintains service integrity, thereby upholding professional ethics and regulatory obligations related to network security and customer service standards. An incorrect approach that proceeds with deployment without adequate security validation fails to meet the due diligence expected of a service provider. This could lead to data breaches, service disruptions, and significant reputational damage, potentially violating regulations concerning data privacy and service-level agreements. Another incorrect approach that delays deployment indefinitely due to minor, manageable risks stifles innovation and fails to deliver the promised service improvements, potentially impacting business objectives and customer satisfaction without a proportionate justification based on the identified risks. An approach that relies solely on vendor assurances without independent verification is also professionally unsound, as it abdicates the responsibility for network security to a third party, which is contrary to the field engineer's duty of care and the service provider's ultimate accountability. Professionals should employ a structured decision-making process that involves 1. Understanding the business and technical objectives of the proposed change. 2. Conducting a comprehensive risk assessment, including security, operational, and performance impacts. 3. Evaluating potential mitigation strategies and their associated costs and benefits. 4. Consulting relevant internal policies, industry standards, and regulatory requirements. 5. Making a recommendation based on a balanced consideration of all factors, prioritizing security and reliability. Question 16. Cost-benefit analysis shows that implementing segment routing, SR, with MPLS data plane offers significant improvements in traffic engineering and network scalability compared to the current MPLS LDP-based infrastructure. However, the transition requires substantial training for the operations team and a phased rollout across multiple core network domains, each with unique traffic patterns and existing configurations. Which approach best balances the potential benefits with operational stability and regulatory compliance for a service provider? Option A. Immediately deploy SRMPLS across all core domains simultaneously to realize the benefits as quickly as possible, relying on vendor support for any immediate issues. Option B. Implement SRMPLS on a single router in a production environment to observe its behavior under live traffic, without extensive pre-deployment testing or a formal rollback strategy. Option C. Postpone the SRMPLS deployment indefinitely due to the perceived complexity and training requirements, continuing with the existing MPLS LDP infrastructure. Option D. Conduct a comprehensive proof of concept, POC, in a lab environment, followed by a phased deployment in a non-critical core domain, with extensive monitoring and rollback plans before expanding to other domains. The correct answer is A. Immediately deploy SRMPLS across all core domains simultaneously to realize the benefits as quickly as possible, relying on vendor support for any immediate issues. Explanation. This scenario presents a common challenge in service provider routing where a new technology offers potential performance gains, but requires significant upfront investment and operational changes. The professional challenge lies in balancing the immediate operational stability and cost constraints with the long-term strategic benefits of adopting advanced routing features. A field engineer must not only understand the technical merits, but also the broader business implications and regulatory compliance. The correct approach represents best professional practice because it prioritizes a phased, risk-mitigated implementation that aligns with established operational procedures and regulatory compliance frameworks. This involves thorough testing in a controlled environment, ensuring that any new configuration adheres to existing service-level agreements, SLAs, and security policies. The justification for this approach is rooted in the principle of maintaining service integrity and minimizing disruption, which are paramount in regulated telecommunications environments. Adherence to change management processes, documentation, and post-implementation verification ensures accountability and auditability, crucial for regulatory oversight. An incorrect approach that bypasses rigorous testing and validation or implements changes without proper authorization and documentation, poses significant regulatory and ethical risks. Such actions could lead to service degradation or outages, violating contractual obligations and potentially breaching regulations related to service availability and data integrity. Ethically, it demonstrates a disregard for the impact on customers and the organization's reputation. Implementing a solution without considering its full lifecycle impact, including monitoring and rollback plans, is also professionally unsound and can lead to prolonged instability and increased operational costs. The professional reasoning process should involve a comprehensive assessment of technical feasibility, operational impact, security implications, and regulatory compliance. This includes consulting relevant documentation, engaging with network operations and security teams, and adhering to established change control procedures. A structured approach, starting with a proof of concept and gradually scaling up, allows for early detection and mitigation of issues, ensuring that the final deployment is robust, secure, and compliant. Question 17. Stakeholder feedback indicates a critical customer-impacting routing issue is occurring, causing significant service degradation. The field engineer has identified a potential configuration chain that could resolve the immediate problem, but implementing it would bypass the standard change control and validation procedures due to the urgency. What is the most professional and compliant approach to address this situation? Option A. Initiate the formal incident management process, conduct a thorough root cause analysis, and then submit a change request for the proposed configuration modification, adhering to all validation and approval steps. Option B. Propose a rollback to the last known good configuration without investigating the root cause of the current anomaly. Option C. Immediately implement the identified configuration change to restore customer service as quickly as possible, documenting the change retrospectively. Option D. Implement a temporary, undocumented workaround that mitigates the symptoms of the issue without addressing the underlying cause. Correct answer is C. Immediately implement the identified configuration change to restore customer service as quickly as possible, documenting the change retrospectively. Explanation. Scenario analysis. This scenario presents a common challenge in service provider routing environments where the need for rapid troubleshooting and service restoration clashes with the imperative to maintain network stability and adhere to established operational procedures. The field engineer is under pressure to resolve a customer-impacting issue, but the proposed solution, while seemingly effective in the short term, bypasses standard change control and validation processes. This creates a professional dilemma: prioritize immediate customer satisfaction and service availability, or uphold rigorous operational integrity and risk prolonged downtime. The challenge lies in balancing these competing demands, while ensuring no regulatory or policy violations occur. Correct approach analysis. The correct approach involves a systematic, documented, and approved method for addressing the network anomaly. This aligns with best professional practices for service provider operations, which are often dictated by industry standards and regulatory frameworks, e.g., ITIL principles for incident and change management, which are foundational in many service provider environments. By initiating a documented incident management process, performing thorough root cause analysis, and then submitting a formal change request for the proposed configuration modification, the engineer ensures that the fix is not only effective, but also understood, tested, and approved by relevant stakeholders. This approach minimizes the risk of unintended consequences, maintains network auditability, and complies with operational governance. It demonstrates a commitment to long-term network health and service reliability, which is a core ethical and professional responsibility. Incorrect approaches analysis. Implementing the configuration change directly without following the change control process is a significant regulatory and ethical failure. It bypasses critical validation steps, potentially introducing new issues or exacerbating existing ones without proper oversight. This violates operational policies designed to ensure network stability and prevent unauthorized modifications. It also undermines auditability, making it difficult to trace the cause of future network problems. Proposing a rollback to a previous known good configuration without first investigating the root cause of the current issue is also professionally unsound. While rollback can be a valid incident resolution tactic, it doesn't address the underlying problem that led to the current state. This approach risks the issue recurring and fails to learn from the incident, which is a missed opportunity for network improvement and a potential violation of proactive network management principles. Suggesting a temporary workaround that doesn't address the core issue and is not documented or approved is another failure. Temporary workarounds, if not properly managed, can become permanent, leading to network complexity and technical debt. They also lack the rigor of a formal change, potentially introducing instability and failing to meet service level agreements, SLAs, in the long term due to the unaddressed root cause. Professional reasoning. Professionals in service provider environments must adopt a decision-making process that prioritizes adherence to established operational frameworks and regulatory compliance. When faced with an incident, the first step is always to follow the defined incident management procedures. This includes proper documentation, communication, and escalation. For any proposed solution that involves network configuration changes, the change management process must be followed. This typically involves impact assessment, testing, approval, and scheduled implementation. If immediate action is required to restore service, a documented emergency change procedure should be utilized, which still involves a degree of approval and post-implementation review. The overarching principle is to ensure that all actions taken are traceable, justifiable, and contribute to the overall stability and security of the network, thereby protecting customer services and meeting contractual obligations. Question 18. The control framework reveals a widespread degradation in network performance impacting multiple service provider customers. Initial reports suggest intermittent packet loss and increased latency. As the field engineer on call, what is the most effective and least disruptive initial approach to diagnose the root cause? Option A. Begin by meticulously examining the physical layer connections and hardware health of all network devices in the affected path. Option B. Systematically verify the stability and convergence of core routing protocols, e.g., BGP, OSP, and then analyze traffic utilization on key interfaces. Option C. Immediately initiate a deep dive into the specific configurations and customer premises equipment, CPE, of each affected customer to identify individual anomalies. Option D. Implement immediate, minor configuration adjustments on the edge routers to attempt to reroute traffic away from potentially congested links. The correct answer is A. Begin by meticulously examining the physical layer connections and hardware health of all network devices in the affected path. Explanation. Scenario analysis. This scenario presents a common challenge in service provider environments where network performance directly impacts customer service level agreements, SLAs, and consequently, revenue. The field engineer is tasked with diagnosing a performance degradation issue that is affecting multiple customers. The challenge lies in isolating the root cause efficiently and accurately without causing further disruption, while adhering to operational procedures and potential regulatory compliance related to service availability. The pressure to resolve the issue quickly, coupled with the need to maintain network stability and customer trust, requires a systematic and well-informed approach. Correct approach analysis. The correct approach involves a methodical, top-down troubleshooting methodology, starting with the most likely and impactful areas. This aligns with best practices in network engineering and operational support. By first examining the core routing protocols e.g., BGP, OSP, for convergence issues, route flapping, or excessive updates, the engineer addresses the fundamental mechanisms that dictate traffic flow. If these are stable, the next logical step is to analyze the traffic patterns and utilization on the affected interfaces. This allows for the identification of congestion or unexpected traffic spikes. Finally, examining the physical layer and hardware health provides a comprehensive check for underlying infrastructure problems. This structured approach minimizes the risk of introducing new issues, ensures that the most probable causes are investigated first, and facilitates efficient problem resolution, thereby upholding the commitment to service availability and customer satisfaction, which are implicitly governed by service provider operational guidelines and potentially by regulatory requirements concerning service continuity. Incorrect approaches analysis. Focusing solely on the physical layer and hardware health without first verifying the routing protocol stability is a premature and potentially inefficient approach. While hardware issues can cause performance problems, routing protocol instability is a more common cause of widespread service degradation in a routed network. This approach risks overlooking a critical software or configuration issue that could be resolved more quickly. Investigating individual custom-reported issues in isolation without first assessing the overall network health and routing stability is also problematic. This can lead to a fragmented troubleshooting effort, wasting time on specific customer configurations or CPE issues when the root cause might be a broader network problem affecting multiple users. This reactive, customer-centric approach, while important for customer satisfaction, can delay the identification of a systemic network issue. Implementing immediate configuration changes on critical routing interfaces without a thorough diagnosis is a highly risky approach. Such actions can exacerbate the problem, lead to complete network outages, and violate operational procedures designed to prevent unintended service disruption. This directly contravenes the principle of maintaining network stability and could have significant financial and reputational consequences, potentially leading to breaches of service commitments. Professional reasoning. Professionals should adopt a systematic, layered troubleshooting methodology. This involves understanding the network architecture and the OSI model, or a similar conceptual framework. The process should begin with verifying the foundational elements, Layer 1/2, then Layer 3 routing protocols, followed by analyzing traffic flow and congestion, Layer 3/4, and then examining application-level issues or specific device health. Documenting each step, hypothesis, and test performed is crucial for knowledge sharing and future reference. When faced with performance degradation, the priority is to restore service while minimizing further impact. This requires a calm, analytical approach, prioritizing actions that are least likely to cause further disruption and most likely to identify the root cause efficiently. Adherence to established operational procedures and change control processes is paramount. Question 19. Cost-benefit analysis shows that implementing a new traffic engineering protocol could significantly improve network utilization and reduce latency for critical services. However, this protocol is relatively new to the service provider market, with limited widespread deployment and a less mature ecosystem of supporting tools and expertise compared to established protocols. Field engineer is tasked with recommending an implementation strategy. Which of the following strategies best represents a professional and responsible approach to introducing this new protocol into the production network? Option A. Conduct extensive lab testing and a controlled pilot deployment in a non-critical segment of the network, gathering performance data and operational feedback before a wider rollout. Option B. Prioritize the protocol that offers the lowest initial licensing cost, assuming that operational complexities can be managed as they arise. Option C. Implement the new protocol only on edge devices where its impact is isolated and less likely to affect the core network's stability. Option D. Immediately deploy the new protocol across the core network to realize the full benefits as quickly as possible, relying on vendor documentation and initial testing. The correct answer is D. Immediately deploy the new protocol across the core network to realize the full benefits as quickly as possible, relying on vendor documentation and initial testing. Explanation. This scenario presents a common challenge in service provider network design, balancing the immediate need for increased bandwidth with the long-term implications of technology choices, particularly concerning the operational and security implications of adopting new protocols. The professional challenge lies in evaluating not just the technical performance, but also the broader impact on network stability, manageability, and adherence to established operational procedures and security policies, which are implicitly governed by industry best practices and potentially by service-level agreements, SLAs, that mandate certain levels of network resilience and predictability. The correct approach prioritizes a phased, well-tested implementation of a protocol that has demonstrated maturity and interoperability within the service provider ecosystem. This aligns with professional best practices by minimizing risk, ensuring thorough validation, and allowing for incremental adoption. It reflects a commitment to network stability and operational efficiency, which are paramount in service provider environments where service disruptions can have significant financial and reputational consequences. This approach implicitly adheres to the spirit of responsible network engineering, which emphasizes due diligence and risk mitigation before widespread deployment of unproven or less mature technologies. An incorrect approach that immediately deploys a protocol without sufficient testing or understanding of its operational impact introduces significant risks. could lead to unforeseen network instability, increased troubleshooting complexity, and potential security vulnerabilities if the protocol is not properly secured or if its implementation introduces new attack vectors. Such an approach fails to uphold professional responsibility by prioritizing speed over thoroughness, potentially violating implicit SLAs for network uptime and performance. It also risks noncompliance with internal operational standards and security policies that mandate rigorous testing and validation of new network elements and protocols. Another incorrect approach, focusing solely on the lowest initial cost without considering long-term operational expenses, maintenance, and potential vendor lock-in, demonstrates a failure in comprehensive cost-benefit analysis and strategic planning. This can lead to higher total cost of ownership and hinder future network evolution, which is a failure in professional foresight and responsible resource management. The professional decision-making process for similar situations should involve a structured risk assessment, a thorough evaluation of technical merits against operational realities, and a consideration of the long-term strategic implications. This includes pilot testing, phased rollouts, comprehensive documentation, and training for operational staff. It also requires adherence to established change management processes and a clear understanding of how any new technology impacts existing security postures and service commitments. Question 20. Quality control measures reveal intermittent packet loss and increased latency affecting a critical customer segment. The network engineer must diagnose and resolve this issue on a multi-vendor service provider backbone. Which of the following troubleshooting approaches is most aligned with best practices for minimizing service disruption while ensuring accurate root cause identification? Option A. Focus troubleshooting efforts on the customer's premise equipment and their direct connection to the service provider's network, as this is the most likely point of failure. Option B. Immediately escalate the issue to the core network engineering team and request a full network topology review and configuration audit. Option C. Begin by performing a comprehensive packet capture on all affected customer-facing interfaces and then analyze the captured data for anomalies. Option D. Systematically verify physical layer connectivity, check routing protocol adjacencies and state, examine forwarding tables for correct entries, and then use targeted ping and traceroute tests across the suspected path. The correct answer is C. Begin by performing a comprehensive packet capture on all affected customer-facing interfaces, and then analyze the captured data for anomalies. Explanation: scenario analysis. This scenario presents a common challenge in service provider environments where network performance directly impacts customer satisfaction and revenue. The challenge lies in identifying the root cause of intermittent packet loss and latency in a complex, multi-vendor routing environment without disrupting ongoing services. The field engineer must balance the need for rapid resolution with the imperative to avoid further service degradation or outages, all while adhering to operational procedures and potentially service-level agreements, SLAs. The pressure to restore service quickly can lead to hasty decisions, making a systematic and data-driven approach crucial. Correct approach analysis. The correct approach emphasizes a methodical, layered troubleshooting methodology, starting with the most probable and least intrusive causes. This aligns with best practices in network engineering and is implicitly supported by operational guidelines that prioritize service stability. By first verifying physical layer integrity and basic connectivity, then examining routing protocol adjacencies and traffic forwarding, the engineer systematically eliminates potential issues. Analyzing traffic patterns and utilizing diagnostic tools like ping and traceroute at various points in the path provides concrete data to pinpoint the problem. This data-driven approach ensures that interventions are targeted and effective, minimizing the risk of unintended consequences. This aligns with the ethical obligation to provide reliable service and the professional responsibility to maintain network integrity. Incorrect approach is analysis. One incorrect approach involves immediately assuming a complex configuration issue and making broad changes to routing policies without sufficient diagnostic data. This violates the principle of least privilege and can introduce new problems or exacerbate existing ones, leading to service outages and potential SLA breaches. Ethically, this demonstrates a lack of due diligence and a failure to uphold professional standards of care. Another incorrect approach is to focus solely on the edge devices without considering the core network or intermediate transit providers. This is a failure to conduct a comprehensive investigation and can lead to misdiagnosis and prolonged downtime. It neglects the interconnected nature of service provider networks and the potential for issues to originate outside the immediate control domain. This can also lead to contractual disputes if SLAs are not met due to an incomplete investigation. A third incorrect approach is to rely solely on anecdotal evidence or the reports of other teams without independent verification. While collaboration is important, network troubleshooting requires objective data. This approach risks propagating misinformation and delaying the identification of the true root cause, potentially leading to significant financial and reputational damage for the service provider. It also fails to meet the professional standard of rigorous problem solving. Professional reasoning. Professionals should adopt a structured troubleshooting framework. This involves 1. Clearly defining the problem and its impact. 2. Gathering all available information including logs, monitoring data and customer reports. 3. Forming hypotheses about potential causes starting with the simplest. 4. Testing hypotheses systematically using appropriate diagnostic tools. 5. Implementing solutions based on verified data. 6. Verifying the resolution and documenting the process. This methodical approach ensures efficient problem solving, minimizes risk, and upholds professional integrity.